actions within the compiler. Let's open this directory. Here we can see an additional folder called as quick. If we navigate to this directory, we can additionally see more files over here. The main ones will be the calling convention.cc and the JNI compiler.cc. This is the actual code for the JNI portion. If I go back to the compiler directory, I can also see a directory called as linker. This linker directory contains the functionality related to linking the compiled machine code with the other components in the Android runtime. Android implements a lot of optimization techniques such as inlining, constant folding, dead code elimination, and a bunch of them. You can find the code for it in the directory called as optimizing. If we look at this directory, we can see the code for all of the optimization that is being performed. For example, we can see a file called as deadcodeelimination.cc over here. We can also see files like loadstoreanalysis.cc and the licm test.cc over here. Going back to compiler, here we will see a directory called as utils. Utils, as the name suggests, contains the utility functions and the common helper code used across the various different parts of the compiler. So over here you can see the utility code like assembler.cc, jni macroassembler.cc, and dedupe settest.cc. We can also see prototype files like stack_check.h. Now let's go back to the original ART folder. We'll not go through all of these directories, but you can see a lot of folders that can help with the Android runtime over here. For example, there is a folder called as ADB connection. This folder contains the code for managing connections over the Android debug bridge. Then there is a directory called as RD. RD provides a RD daemon that manages the various background operations for the Android runtime. You can see its source code here inside the RD directory. To learn more about it, feel free to click on the load more button over here and it will talk about the additional system properties over here. Then if I go back into the art folder, I can also see a directory called as build. The build directory is going to contain all of the build scripts and configurations that are related to the Android runtime. This includes things like the make files, cmake, and other files. By clicking on load more over here, you can learn how to actually build the ART module. Then we have something called as dex2oat. Dex2oat is used by Android runtime to perform the ahead of time compilation, which is converting the dex bytecode that is used by the Android application package into native machine level code that is optimized for the target CPU architecture. So the dex2oat directory will contain the code for this .dex to .oat converter. .oat or .oat are basically the ahead of time compiled code. The most important file over here is going to be the dex2oat.cc. We can scroll down over here to understand the complete working of the dex2oat utility. In addition to dex2oat, if I go to the ART folder, I can also see a directory called as dexdump. Dexdump allows developers to inspect the contents of a .dex file. It can show the structure of the dex file, including the class definitions, the methods, and other metadata that is useful for debugging or reverse engineering the application. You can find the source code for the dex2dump utility right over here. The most important file over here is going to be the dexdump.cc file. Let's again go back to the art folder. Let's talk about a few different directories over here. Over here, we have a directory called as libelfile. This libelfile directory provides the utilities for working with ELF files. ELF is mostly used in Android for the native executables and the shared libraries. The blueprint file for libelf is going to be present over here in android.bp. In addition to it, we have a few directories over here. If I click on ELF, I can see the code for elfbuilder.h. I can also see the elfutils.h over here. Then there is a directory called as libnativebridge. The libnativebridge directory provides the support for bridging between the Android runtime and the native code. It basically implements the native bridge functionality, which allows the Android runtime to run native code that is compiled for a different CPU architecture. This is important in systems where applications need to run legacy native libraries not originally compiled for the current hardware architecture. Then we have a directory called as libnativeloader. This directory contains the code that is responsible for loading the native libraries in Android. Basically, it manages the loading and linking of the shared libraries, which is going to be the .so files that are used by the Android applications. If you want to learn more about the libnative loader, click on the load more over here and go through the content that is present over here. You can also see about the implementation details in this readme file. Now I'll go back into the art folder. One more directory of interest is going to be the oat_dump directory. Oat_dump is basically a diagnostic tool that reads .oat files and dumps the human readable information about the files. This could include information such as its structure, method information, and the optimization details. The source code for the oat2dump utility can be found inside the oat2dump directory over here. Here you can see the Android blueprint. You can also see the oat_dump.cc, which is going to be the most important file over here. Then we see a directory called as runtime. This runtime directory contains the core implementation of the Android runtime. This includes the code for the interpreter, the JIT and the AOT compilers, things like garbage collection, threading, signal handling. It also includes things like the class loading and runtime error handling. For example, if we look at the GC directory over here, you can use the source code over here to understand how Android performs garbage collection. Back in art, you can also find a directory called as tools. In the tools directory, you can find the source code for a bunch of familiar tools that you might have seen before. For example, you can see dexfuzz over here, you can see jfuzz, you can also see signal dumper as well as dex analyze. The tools directory will contain the code related to all of these. So this was a rundown on the various directories that we can see inside the art directory for AOSP. Now let's go back into the root folder to look at the other directories that are available. The next one that we'll be looking at is going to be the Bionic folder that we see over here. The Bionic directory contains the Android-specific implementation of the C library, which is going to be libc, as well as the dynamic linker and the threading libraries. I'll just open this directory. You can read all that you want about the Bionic implementation by clicking on the Load More button over here. It'll tell you about the various lib implementations that we see. For example, we see libc, libm, libdl, and a bunch of it over here. It then talks about the details of libc, which is going to be very important as it corresponds to Bionic. I'll go back into the Bionic folder again. Inside the Bionic folder, we can actually see additional directories. One of it is going to be the libc folder. This libc directory contains the source code for the C standard library. It essentially provides the functions for basic tasks such as file input-output, string manipulation, and math operations. Back in Bionic, we can also see an additional folder called as linker. The linker directory includes a dynamic linker code. Android's dynamic linker is responsible for resolving and loading the shared libraries, which is the .so files at runtime. We can also see a directory called as tests. The test directory contains the unit tests for the Bionic library. Now let's go back into the default root directory. The next directory in the AOSP folder structure is going to be the bootable directory. The bootable directory includes the components that are necessary for the boot process of Android devices, such as the bootloader and the recovery mode. If I open the libbootloader directory, here I can see an additional directory called as gbl. This gbl directory contains the generic bootloader library. You can see the instructions on how to build this library if you click on the Load More button over here. You will notice that this is basically a Bazel workspace. Back in the libbootloader directory, we can also see an additional directory called as libxbc. This stands for Extended Boot Control. This directory will contain some boot control and boot image management operations. Let's actually open the libxbc.file. If I scroll down, the comments will point us to the actual boot control and the boot management operations that we see. If we go back into the bootable directory, we can also see one more subdirectory called as recovery. This recovery directory will contain the information related to the recovery images. Now that we've looked at the bootable folder, let's go back into the root folder for AOSP. The next directory that we will be looking at is going to be the build folder. This directory contains the scripts and the make files that are used to build the Android operating system. Let's actually open this directory. Here you can see a bunch of additional files. For example, you can see a file called as envsetup.sh. This file is a symbolic link for make/envsetup.sh. If we look at this file, what we will notice that this script sets up the environment for building Android. It basically defines the environment variables that are used by the build system and also sources the other scripts inside the build folder. Then we have a directory called as core. This core is a symbolic link for make/core. This directory contains the scripts and the make files that are used to build the core components of the Android operating system, such as the kernel, the bootloader, and the system images. Now let's again head back into the build directory. Here we can see a directory called as target. This directory contains the configuration files for building the Android system for specific hardware targets. Each of the target folders will correspond to specific devices or emulator configurations. If we click on the board folder that we see over here, we can see a bunch of possible targets. Let's select, for example, the generic _ARM64 directory. Here we can see a bunch of files. The board configuration.mk file contains the board specific configuration settings such as the CPU architecture, memory size, display resolution, all of that information. Then the next file inside the generic ARM64 directory is going to be the devices.mk file. This device.mk file contains device-specific configuration settings such as the kernel image and the root file system image that are used for the target. Back in build, one more thing about the target directory over here is that the target folder is not used during the normal build process. It is used by the launch command to select the target for a build. In terms of directories, we can also see a directory called as Soong over here. It basically makes use of blueprint files, which are going to be the .bp files. You can read more about it by clicking this button over here. All of the information related to Soong is going to be present over here. Like I said, the most important file is going to be the blueprint file. We can see the blueprint file over here. The blueprint file basically defines the build rules in a declarative manner. Then inside the build directory, we can also see one more subdirectory called as Bazel. Bazel is the newer build system developed by Google. It is used to compile and link large projects like the Android platform itself. The best part about Bazel is that it is known for its speed and ability to scale across very large code bases. Now that we've looked at the build directory, let's go back into the root of the AOSP project. The next directory that we are interested in is going to be the CTS directory. CTS stands for Compatibility Test Suite. This is basically a testing framework that ensures device compatibility with the Android platform. CTS verifies that the device meets the Android compatibility definition document, which is going to be the CDD requirements. Inside the main CTS directory, you can find one more subdirectory called as apps. This directory will contain all of the CTS test applications. These applications are used to test specific Android features such as the camera and others. Then back inside the CTS directory, we can also see one more subdirectory called as host side tests. These are going to be very important if you want to run the CTS test on a host machine. The last directory inside CTS that we will be talking about is going to be the test directory. This directory contains the CTS test scripts. These scripts are used to run the CTS tests on any device under test. Now that we've discussed about the CTS directory, let's head back into the root AOSP path. Here we can also see a directory called as Dalvik. This Dalvik directory contains the source code for the Dalvik virtual machine, which was a predecessor to ART. Let's look at this directory further. Here we can see a subdirectory called as DexGen. The DexGen subfolder contains the source code for the DexGen tool, which is used to generate Dex files from the Java bytecode. Then inside the Dalvik folder, we can also see one more directory called as DX. This DX subfolder contains the source code for the DX tool, which is used to convert Java bytecode into the Dex files. Now let's head back into the root directory again. Here we can see a directory called as developers. The developers directory includes the resources and tools meant for developers who are building or modifying Android. This directory is less frequently updated but contains important developer-centric documentation as well as samples. If you go to the samples folder over here and click on Android, you can see a bunch of code information over here. This is going to be very important to developers. Now I'll head back into the root directory again. The next USB directory that we will be looking at is going to be the development directory. This directory contains the tools, utilities, and the sample code that are useful for the Android platform developer. It includes testing tools, debugging utilities, and other sample projects. If I open this directory, I can see a bunch of additional subdirectories over here. For example, if I go into the apps directory over here, I can see a bunch of development applications present over here. The next directory that we will be looking at is going to be the device directory. The device folder contains device-specific code for the AOSP project. This code includes the drivers, kernel modules, and other files that are specific to a particular device. This device code is used to make the AOSP project work on the specific devices that are listed over here. If we go to the Google subdirectory, we can see a bunch of additional device-specific information over here. For example, we have Ravioli. Ravioli points to Pixel 6 devices. We also have the Ravioli kernel over here. In addition to this, we can see Lynx over here. Lynx is going to be a Pixel 7a device. Anger Pro is going to be a Pixel tablet. Cuttlefish is your Android emulator. So basically, this directory will contain all of the configurations that are required for Google devices. Let's say, for example, I'm opening Ravioli for Pixel. Here you can see all of the device code that is going to be important for Pixel 6 devices. For example, you can see the board information over here. You can see the AOSP MK files. You can also see all of the make files that are going to be important. We can also see some important directories like the factory images Raven. This one has a simple shell script over here. Just like Google, if I go back into the devices, we can also see the code for Lenaro as well as generic devices. Now that we've looked at the device folder, let me head back into the root directory for AOSP. Next, we can see a directory called as external. This directory contains the open source libraries that are used by the Android platform. These libraries are not primarily developed or maintained by the Android AOSP project, but are essential for providing certain features on the Android devices. For example, you can see the code for AFL++ over here. If I scroll down, I can see the code for jmalloc new over here. You will also find the standard things that you would otherwise expect like protobuf, pthreadpool, Python, and other information in this same external directory.